Crash helmet design, prototyping, and testing. Define phase. In this portion of the define phase, we're actually going to be focusing only on measurements which we need to take. So let's examine what needs to happen during this phase, specifically with regard to those measurements. Remember, the entire design thinking process moves from empathize to define, to ideate, to prototype, and finally to test. So in the define phase, we are defining the problem, and our goal is to create a good problem statement which guides our team. The statement needs to be human-centered. It focuses on the people that we learned about in the empathize phase rather than the monetary returns or the product specs. It needs to be broad enough for creative freedom. Don't focus too narrowly on a very specific method regarding the implementation of the solution. Don't dive into an answer right away. But at the same time, that problem statement still needs to be narrow enough to make it manageable. If you just say, I want to feed the world, that's just too big. So we need to keep it somewhat narrow. And we need to have sufficient technical requirements to make the problem solvable. Ultimately, we'll begin the problem statement with an action-oriented verb. And we'll be talking more about exactly how to write that statement a little bit later on. So in this project, we are concerning ourselves with developing a protective device for the human head in order to prevent, minimize, eliminate traumatic head or brain injury. But we're obviously not going to be using real human heads. We're going to be simulating the human head. So an egg will simulate the human head in this project. But we need to define many different components of this. So first we need to define, is this going to be an ostrich egg, a chicken egg, or some other type of egg? I'm guessing most of you will lean towards chicken eggs. Will the egg be raw or boiled? I would strongly suggest boiled simply because it will make a lot less of a mess. But it is your choice. The orientation of the egg. Will you be orienting it with the point down or the point up? This shape appears to be a little bit more like a head, but maybe there's some practicality about dropping this that we need to consider with regard to orientation. Shape. Where will this protective helmet be worn? If we orient the egg this way, and this is the top of the head, then we really have more of a rounded hemispherical shape. On the other hand, if we orient the egg this way, with this pointy part up, we have more of a paraboloid shape. And we can take a little bit closer look at each of these shapes in 3D. We also need to consider the mass of an egg. Now obviously, in any dozen of eggs, in any dozen container, there's going to be many different masses. Each egg is going to have a different mass. So we're going to need to make some decisions about what mass we'll use for our computations, which will come later on. But for now, what we'll need to do is just have a simple kitchen scale and measure the mass of several eggs in grams. Then we'll need to measure the dimensions of the eggs. The diameter, the circumference, the length. What are the ways in which we can quantify the size of this egg? And I think what makes most sense is to measure the width here, from which we could compute circumference, but using calipers we can measure that width, and the length from here to here. And we have calipers in the lab which you will be using to make those measurements in millimeters. And lastly, another attribute we need to define is the shell itself. What are the material properties of the shell? Its thickness, its brittleness, and the conditions under which it will crack. We'll ultimately be using a measuring tape in order to measure drop distances and determine those distances with regard to cracking when we drop the egg. Now, to make your measurements, each team of students will consist of 2 to 4 individuals, and each team will need to bring to school a dozen eggs. It's up to your team to determine the size of the eggs, medium, large, etc. and whether they're raw or boiled. Boiled is preferable, less messy, less smelly, but obviously that decision may impact your results. Later, during the prototype and test phases, each team will also again need to bring one additional dozen of eggs of exactly the same type that you brought previously. So, same size and same condition, raw or boiled. Now, step one. This first set of measurements that you will be making consists of recording the egg masses. What you'll need to do is take each egg, one at a time, place it on the kitchen scale, and record the number of grams for that egg. Remember, mass is a measure of inertia. It does not change dependent on where we are. If we're on Earth, our mass is the same as if we are on Mars, as if we are on the Moon. The mass of the egg is consistent and is the same everywhere. Force is different. Force is the product of mass and acceleration. Therefore, the acceleration due to the gravitational force on that particular celestial body will change the force. So we do not use the term the weight of the egg. We use the term the mass of the egg. And note that the units are grams. Let's take a little bit closer look at how we're going to make these measurements, and specifically how we're going to record them in a spreadsheet, plot them, and then determine the minimum, the maximum, and the median number of grams for our eggs. So the next step after we have massed each egg is to record in Google Sheets each of those masses and determine the minimum, the median, and the maximum. Let's take a look. Open up Google Sheets and create a new spreadsheet called Egg Measurements. Since I made my measurements on grade A large eggs, I went ahead and specified this as well. In your first column, label the column egg number, and then number each of the eggs, 1 through 12. In column B, we'll label this mass raw, and the units are grams. Now, here I've made the numerical measurements, and I have recorded each one from the kitchen scale in my spreadsheet. You'll notice I've used 1 decimal place. If you want to format the number of decimal places, you simply highlight the cells and then go to Format, Number, and you can select these different formats, including more formats, custom number format, and then depending on how many positions you put after the decimal place, it will increase that specificity. So for instance, if I put 2 positions after the decimal place and apply, you'll notice it added that additional decimal place. I just undid that though because it's really not practical to think that I'm going to have that level of precision on my measurements. Even 1 decimal place is iffy. But if the scale shows you this, then let's go ahead and record it as such. So for each egg, I've recorded the raw mass in grams. And now what I'd like to do is I can just go ahead and plot this data. So again, I'll select the title and all of the data in the column. And I can press my Insert Chart, and it will graph it for me. Now I need to make some changes. This is a column chart. That's really not appropriate for this data set. I really want something more along the lines of a scatter plot. You'll also notice that it looks as though my data is wildly all over the place, and yet by looking at it, it looks as though it's fairly consistent in terms of the number of grams. That is because the chart is not scaled appropriately. So if I go to Customize, Vertical Axis, and let's change the minimum on the vertical axis from 0 and the maximum on the vertical axis to 100, then this looks probably like a better presentation, a more appropriate presentation of the data. Okay. So my 12 eggs are plotted here. I can adjust the chart a little bit. I can also, again, add, for instance, a title on the chart, set the axis title, set the chart title. I can make this say mass of raw eggs, and I can note that it's in grams. Entirely up to you. You can adjust and change the parameters of the chart, but I believe this is sufficient for now. Okay. Now, the masses are, of course, in order of how I recorded them. I can sort those numbers. So what I'd like to do is I'll just select that data again. I'll copy it. And I'll go here and I'm going to paste, but I will paste special. I just want to paste the values because I want the values there, but I want them kind of dissociated from the original column in which I recorded them. Otherwise, every time I make a change here, it will make a change here. And what I want to do with this data set is I want to sort it. I can sort it in increasing or decreasing order. If I go to data, sort range, let's see, and it asks me how do I want to sort this custom range in column G. That's the correct column. I can go A to Z or Z to A. I want to go A to Z because that implies increasing. So if I go sort, now I've got my minimum number here and my maximum number, my maximum mass here. Okay. Let me move over a little bit. I've labeled one more column, minimum, maximum, and median. So what I'd like to do now is actually just have it select those numbers for me from the chart. Now I can see what the minimum is and I can see what the maximum is, but if I had a data set of 5 million data points for items sold and their prices on Amazon, that might not be as practical. So let's actually have the spreadsheet do the computation for us. So I've just put the label minimum here, and in this next column, if I just put equals and then type in min, you'll see that it will offer me a computation that I can perform, opens the parentheses, and I'll select the range of cells, close the parentheses, and press enter or return, and it will pull that number up for me. Let's do the same for maximum. Okay, equals max. Okay, so pulls it right up, opens the parentheses, select the same range, and press enter. There it is. Now median's a little different. Median is not a mean, it's not an average. It means it's selecting the middle number. And the reason we're going to use median instead of mean is that if we have an outlier, something that's very small or very large, it will skew our data. So a better representation of the midpoint is to find literally the midpoint of the data, the median number. If there's an odd number of data in our set, then it will pull the middle number. If there's an even number, then it will average the two in the middle. So since we've got 12 eggs and none of them had previously cracked, and I was able to obtain data for all 12, it's going to average the two middle numbers. So let's have it perform the computation, however. Med, okay, so it pulls up the median formula from which data set. Again, I'm just using my mouse to highlight those cells, close the parentheses, and it's also specifying specifically which cells, G2 to G13. This is G2 through G13. Enter. 55.7, and that makes sense because these are the two middle numbers, the 55.5 and the 55.9 grams. It takes the average and specifies those as the median. So now I have a little bit of a sense of what this data looks like for the masses of my eggs. For my dozen that I measured, the minimum mass was 50.1 grams, the maximum was 59.9, and the median mass was 55.7. Again, this is being measured in grams. Later we may make a conversion to kilograms, so be aware of how you've made your measurements and the units that you've used. Now, continuing on with our measurements, we need to measure and record the egg dimensions. What does that mean? Well, we know that we're going to be creating some sort of a helmet for this egg, so we're thinking something round, there'll be a diameter and a circumference involved, and that's true. But practically speaking, we're going to use a little tool called calipers to measure the eggs in our dozen. So what really makes the most sense is to measure the width across the widest part of the egg and the length end to end of the egg in millimeters. So you're going to create a data set with your measurements, a scatter plot, sort your data, and compute the min, max, and median, just as you did before when you worked with the masses of the eggs. Remember though, now we're talking about egg dimensions, so we're going to be using a different type of unit. This unit will be millimeters. And again, later on when we make calculations involving the dimensions, we may need to make an adjustment and convert those millimeters to meters. Here's a little bit closer look of what it looks like to use the calipers to measure the width across the widest part of the egg and the length from end to end. Okay, we're ready for our last set of measurements. We'll be measuring and recording the crack conditions of each of our eggs in the dozen, meaning that we're going to be dropping them unprotected onto a hard surface and finding out what's the altitude at which they crack. Again, we're going to be collecting our data, creating a plot, a little bit different format this time, and examining the min, max, and median of our data. Let's take a look, though, at this specific setup. We need a measuring tape or ruler, and we will place it vertically against a wall. We need the hard surface onto which we'll be dropping the egg. We need each egg, and again, it can be raw or boiled, point up or point down. You just need to be consistent. And then from tip to floor is what we'll measure as the drop distance. You will start at 50 millimeters. Drop the egg. If it's uncracked, increase the drop distance to 100 millimeters. If it's uncracked again, increase it to 150 millimeters. So each time you are bumping up that altitude by 50 millimeters. And you continue repeating this process until the egg cracks. At that point, record the altitude when the egg cracks. Again, you're making your measurements in millimeters. And record all your data in an additional tab on your spreadsheet. So here is our additional tab on the spreadsheet at which we are measuring the crack altitude. So here the egg cracked at 150 millimeters, here at 100, and you don't have to have necessarily a correlation between which was egg 1 and which was egg 12 from before. For consistency, it would be ideal actually to label the eggs, and you could possibly look at some interesting correlations across the data, although that's really not the purpose of this particular activity. But just ensure that you bump up each incremental measurement by 50 millimeters. And once you obtain your data, you again will be plotting it. In this case, instead of using a scatter plot, I used a bar chart that seemed to make more sense visually as it's more representative of the data, thinking in terms of those drops, but also adjusting the scale and going from 0 to 250 millimeters, something that was above my maximum. And again, finally looking at the min, max, and median number of millimeters at which the egg dropped, cracked, and in its unprotected state was no longer viable. So that will be your final sheet in your spreadsheet. You've now completed the measurement portion of the define phase. Your measurements have provided you data that you can use to further define your egg client. And in completing the define phase, you'll be making computations about your egg when it falls. You'll quantify velocity, momentum, acceleration, force, drop time, and impulse. And then you can write a problem statement about the protection that you want to design for the egg. Exciting, right? Remember, the point of the define phase is to create an action-oriented problem statement. We'll continue down that path in the next section.